Hello, everyone. Good afternoon. Um, in this talk, we'll take a comparative dive between gRPC and another protocol called ttRPC. We'll look into the protocol itself, understand the key differences, and also see how they fare with respect to each other. I'm Archana, and this is my co-speaker, Sudipta Pandit. We work at Microsoft with a team called Azure Linux, and let's get started.
Um, so, first of all, we must know, because it's a newer protocol, what is ttRPC. And first of all, why are we talking about in gRPConf? It's not even gRPC. I think gRPC was created almost 10 years ago, although the 1.0 version might released a little bit later, almost 8 years after that. It's been quite in cloud native space. We've seen its implementation quite ubiquitously, and mostly in microservice distributor system and microservices. Between microservices interprocess, the inter-service communication, we can see its most wide uses. But one of the things gRPC chose when it's creating, when they designed it, is that they chose it to build it on top of HTTP2, which is great. It has many features and it's like a newer protocol. But it comes with overhead of protocol being with so many features, and also it comes with overhead whenever you want to use the gRPC, you are indirectly using HTTP2. Thus, like whenever you are implementing in a runtime or any system, you are loading the libraries of HTTP2 as well. Which so the newer ttRPC protocol is intended for a low memory and low latency environments. It was designed with that specification that wherever the requirement is for lower memory footprint and lower latency, and while for most of our gRPC use cases, you see that it might not be the requirement to have a really low memory footprint or really low latency footprint. But let's say when you are using it in an environment where there in a single host there are multiple services, they are talking to each other, and or in a very memory tight constrained environment, in that case it could become a problem for using gRPC, because it comes with overhead. Of course, it has features. And also, this ttRPC is designed to mostly in an inter-service communication. It's like service to in a backend environment where in a distributed system, mostly in the same host, or you can say it's a same network behind the firewall, and you are communicating between them. In that case, it is designed for. And because it's designed in that way, we can see that we can remove the HTTP2's some of this layer, because we don't need generally in a similar same network environment or the same host, connections are pretty stable because the network is not traveling over the globe. So, and ttRPC currently has a support for Golang and Rust. Currently, of course, it is not as widespread as gRPC. gRPC has support for like almost most of the popular languages we know, and I think official support for most of the popular languages, even unofficially maybe much more. But of course, when this protocol was designed to cut down some of the features of gRPC to make some of the trade-offs for better memory and latency implementations, it assumes that it has to be in a reliable connection environment. That means you cannot deploy it across the globe where connection could be broken very easily. It also removes the HTTP2, so it does not have your standard features of a HTTP2 protocol like handshake, resets, pings. It actually even removes flow control. Also, TLS is removed for, because we'll be running in the same host environment, so it is assumed when designing this protocol that we will be running behind a firewall, so we might not need security features of TLS. Uh, so let's see who uses ttRPC. We just want, wanted to know who used it. So we went to GitHub repos of this too. We found out, okay, most of many companies directly, indirectly. Above, we listed companies who are directly using it, and indirectly many more who are using mostly containerd. Containerd is very popular, so there are a lot of projects who are built on top of containerd, and those are using it. Now, okay, so let's understand the differences in the protocol stack and how it differs to HTTP, like HTTP2. Like because gRPC is built on HTTP2, will define how this protocol has cut down to a slimmer version. So we mapped the gRPC protocol in top of HTTP2's TCP/IP stack. As we learned, the ttRPC did some of the trimming of this protocol to make it slimmer, make it more simpler. So it can be used in a, it can gain some benefits over the gRPC. So let's first of all we see the network and transport layer. It is quite same. Of course, we didn't. It will be very hard to remove these two layers. I think the last time we saw the Quake tried to, replace the TCP part, like the transport part of it, but it had to do it on UDP because these two layers are kind of standard. Or like replacing this means replacing all the hardwares who are going. So, well, that was kept same because it won't be very hard to do that. And as we discussed that we will be running mostly, this use case is mostly behind a firewall use case, so TLS can be removed. And most of his HTTP, so now we are left with the application protocol, application layer, and most of the HTTP2's features and all these features of channels, frames, comes in its binary framing layer, where you have like headers are frames, also data payloads are frame. As we discovered, we are trimming down it, making it more simpler. So that part of it replaced with the message framing. But we kept the protobuf as well, because protobuf is in ttRPC is used for generally only for serialization, deserialization part of it. In the specification of this protocol, it does not define specifically how the routing logic for RPC is. So RPC part of it is still the same. I mean that in gRPC also RPC routing of the RPC, which method or which service to invoke, it is done. It is the similar in ttRPC. It does not define in the specification. It just tells the implementation has to do it in a way that it is possible to route based on the service name and the method name. So it is up to the implementation. The standard implementation that ttRPC did was in the Golang. Then later on, people from Alibaba, they started using it for Rust as well. So now it is officially incorporated in the containerd projects as well. So now let's understand how it. Now we've seen that okay, we replace the binary protocol with much simpler message framing protocol, and this is the message frame it will look like. And as you can see that it's like a 10-byte header on the message frame. So first 4-byte data length, stream ID, and your message type and flags. These I will come back to it. What is when we explain how the protocol communicates. So let's understand how this protocol works over a streaming request and response. As you can see, this is for a ttRPC stream where client and server both are doing streaming request and response. So in the client will first, in this streaming scenario, client will first send a request payload, and that will come up with a remote open flag. These remote open, remote close, these flags are, if you see, go back, we can see that these flags are in the like message. There are two things: message types and flags. So remote open means that whenever server receives a payload with a remote open flag, that means this for server the remote is the client and client is open for sending more data. So you can simply think of the remote open as means the server is expecting more data. It's open for more data. So you get another payload. If it's empty flag, it will be remote open. Now once we receive the last data payload with the remote close flag, the server knows that okay, it's done with the remote close. And implicitly it also means local close. Local close means locally the client will not produce more in data. That local close part is kept on the global implementation just to maintain the state of the client and server. Once the server receives the remote close, it knows that okay, client is done sending all the streaming data. Now it starts sending the response data. It's like I'm here showing a bidirectional stream, so it will start sending a response. Whenever it sends with the remote close flag, it will now the server when sends the remote close flag, that means server is done with the data response and both of the client and server will become in a finished state. So this finished implicitly means also remote closed, because that means that other peer is not going to send any more data. This is it's a client stream, but server just a single response. Similarly, but the response payload, if you the message type is response, it implicitly means it's also the last payload remote close state. So it becomes in a finished state very quickly. And if we go to Unity stream, it's very simple. In Unity, you don't send any flags. That automatically server assumes it's a single request. As you can see, the protocol is pretty simple, and we just this is the specification we talked about, but we wanted to see how it actually behaves over the wire. So we capture the packets, and so this is for a ttRPC single Unity call. So you can see that okay, it's for a single Unity call. It's like just sends 10 packets, and although most of the TCP handshakes also, it's like it takes a single turn and sends one data packet from the client and one from the server back. Total is around 80 bytes communication, and if you compare that with the gRPC, it's of course it's more, but as I said, it comes with a lot of features. It has HTTP2 comes with window upgrades and those all other frames, and there are control frames also. But as you can see, it takes 7 turns to complete a single request for the first time, and the bytes which are transferred is also higher. It's like 380 bytes. Yes, I think we understood what the protocol does and how it behaves on the network. Now I'll give this back to my colleague to explain how we did the benchmarks and what are the results.
Hello again. So why did we benchmark ttRPC and gRPC? We encountered this protocol when we were working with a project called Kata Containers, in which the containerd shim, the Kata shim, talks to Kata agent, which is a runtime agent, via this protocol ttRPC. So we kind of searched, and we found that containerd also supports gRPC, but gRPC is not being used in client part of the agent. So we wanted to see how the two protocols behave in inter-service communication, such as between shim and agent. And we tried to look for metrics, but we didn't find any. So with that motivation, we wanted to explore. We wanted to see performance, and we wanted to see in the context of memory and latency, how does the two protocol behave. So now, in any inter-service communication, minimizing latency is crucial. For our benchmarking methodology, we used very simple protobuf files from the official repos of gRPC and ttRPC. So very simple hello request, hello reply, protobufs. We generated the required binaries and definitions and all. And once we were done, so we created a tool which allows you to specify the concurrency, and it allows you to specify the time for which you want to do the measurement, and it will output the data in terms of, for example, average, median, and P99, P90, and output this to a file as well. So for our measurement, we set up the servers, very simple ones with the protobufs, and we measured the latency. Initially we warmed up the cache with 200 preliminary requests, and subsequently we bombarded the system with 5K requests. So initially you would see that there is a spike. So x-axis represents the request number and y-axis represents the latency in microseconds. Initially you'll see that spike. So despite warming up the cache, you see that there is a spike, but as the system settles down, there is a stabilization. And you can see the plots for ttRPC and gRPC. ttRPC on average gave 100 microseconds of latency, and gRPC gave 150 microseconds of latency. We wanted to see how the trend continues as we give more requests. So for 30K requests, the trend was kind of similar. So we noticed that there is a difference of 50 microseconds on average between the two protocols. But considering that over the wire ttRPC is slimmer, it has lesser round trips per request, we see how that theoretical advantage actually shows up in real world performance. So, yeah. So the next one was memory profiling. For memory profiling, we wanted to use definitions from containerd shim so that we are able to simulate a real world example and see how the two protocols behave in a realistic context. And so we picked up create task request, which is one of the most used service of containerd. So we generated the protobuf files there, and using the server interceptor, we basically measured. So we used Golang's implementation of gRPC and ttRPC, and we used Golang read memstats to get the statistics from Go runtime, which basically has memory allocation and also garbage collection values there. And we used two values. One was sys and the other is heap released. Sys represents the memory which is claimed by Go runtime for the application, and heap released is the memory which is released back to the operating system by the garbage collector. So the effective memory usage comes down to sys minus heap released. This metric essentially represents the virtual memory address space which is allocated to this Go application. Next, we plotted the data for the two protocols, and we did this for 3 different kind of payload sizes, starting from 64 KIB till 4 MIB. On the x-axis, again, there is request number, and on y-axis, you will see Go app memory, that's in MIB. So the lines represent the payload sizes. Sorry, the line represents the trends. And you can see that for lower payload sizes, gRPC performs better than ttRPC. And so this suggests that the core runtime management of memory allocation and garbage collection for gRPC is better for ttRPC. We also wanted to see how this translates in physical memory usage for the two kind of protocols. So we used PSS and RSS values from PMAP tool, and again for 3 different payload sizes. And this is the data that we got. So the red line is ttRPC and blue line is gRPC. So physical memory usage wise, let me show you the next graphs as well actually. Yeah, and you'll see that initially there is like a stable line, which is basically we kept the system idle for 10 seconds, and then we started snapshotting the system every 1 second. To get the physical memory usage for each of the payload sizes and 5K requests. So you can see that physical memory usage-wise, ttRPC performs better than gRPC. So which suggests that there is efficient physical memory usage, and maybe sharing of the library is more efficient. But we can also notice that as the payload size increase, there is almost no difference between the two protocols. So we also wanted to see how that fares out in Rust. We used PSS and RSS values for the Rust implementation. We used Tonic for gRPC, and we used ttRPC Rust implementation. And this is the plot for those two. And in this, we can notice that ttRPC does not perform as well. gRPC is actually memory efficient than ttRPC for Rust implementation. So that was all the data that we got from our benchmarks. What are the takeaways? ttRPC is lighter over the network. It is slimmer protocol. And it has slightly better latency as compared to gRPC. But it is not as memory efficient as one might expect it to be. And so ttRPC in its concept is very good. But looking at the results, we think that implementation could be improved. That was all. From our side, I have attached some references. I've attached the tools that we used for our benchmarking and profiling. That is it. Thank you. Any questions?
So when you say this is for inter-service communication on the same host, so like I believe most of the use cases are service mesh in which a production-based system in which we have thousands of services communicating with each other. So what's the use case, like apart from your use case in which you want to talk about inter-container communications, like what other use case do you feel this would fit as like ttRPC can be chosen over gRPC? Like because for our use case, like most of the services are inter-microservice communication. So
as you said, like service mesh is kind of a one use case that that could be done. I think out of this cloud could use for like a IoT kind of MQTT replacement. I think so that can be done, but of course then we have to look at an external security proxy out of this, even if the IoT use case or other use case wherever you're exposing this ttRPC to the internet, it has to come up with another proxy layer of security or something. That if it's a inter-service communication, anywhere the requirement is, so basically the requirement has to be, if it's already behind a firewall and it would require very low latency implementations, then it could be, then anywhere that it could be used.
And one more question, like there was a mention about in your slide about like binary frame versus the message frame, and when you're using protobuf, then how do you, like when protobuf serialize, right? It's already converting it to some binary frames. Like
yes, I mean the naming of the stuff is like it still uses binary. So the naming of it's like message framing, which like it was done as a, for HTTP2 it's called binary framing, and after like it was named in the ttRPC as a message framing, and how the messages are framed, it still uses protobuf, and it's true that data payload part of it still will be a binary version of the payload. So once you use protobuf, it will convert into a binary representation and then like send it over the network. So yes, there is binary data part of it still binary. Other parts are not converted to a binary.
okay.
Got a question. Has this been played with non-TCP based protocol, probably UDP or maybe reliable UDP?
No, it was not done. Like for, I think even for gRPC they are experimenting with Quick. So maybe one.
It's officially supported, right?
Yes, no, it's not. It's still experimental. I mean, I saw in the repo and there are talks going on. So I think. Anything else? Okay, thank you.